So let's take a look at the remove method for a linked list. Your list interface that I gave you doesn't include a remove method. You don't need to code it for the assignment. But you may need to have it, for example, in the next assignment or the one after, when we're also going to have our linked list as part of our dictionary. Oh, I just told you the answer. So now what we want to do, here's our linked list again. So we've got a linked list, we've got a head pointer, we've got a tail pointer. And this time we want to remove some specific element in the list. Let's say we want to remove C. I never like C. So how are we going to remove this? The first question is, how are we going to find the object that we want to remove? So our signature for our remove method is probably something like public E remove E object. Okay? We're going to remove something, we're given an object, and we want to return an object. I'll talk more about why we have two things that are the same a little bit later. Okay? So we want to remove something. So the first thing we have to do is find the thing that we want to remove. So how are we going to do that? What are we going to use to say, this is the thing that we want to remove? We're going to use a comparable comparison. So we're going to cast current.data to comparable, and once we've done that, I'm just going to write this on the next line, although it should carry on after that period. We're going to compare it to the object we've been given, and if that is 0, then we've found the thing that we're looking for. Okay? A comparable comparison. Remember when we talked about comparing with generics? This allows us to ensure that whoever is using our data structure has overridden the compare to method. If we just use equals, we may end up comparing things based on their memory allocations of the objects, and that's probably not what we want to do. When we used the head equals tail, that's exactly what we're doing, by the way, is here we're comparing whether the memory location of head and the memory location of tail are the same. And if they are, then we know that we're pointing to a single element list. But we don't want to do that generally. We want to make sure that the people that use our data structure write a compare to method. Okay. So once we've found the thing that we're looking for, the way that we delete it is we take the node before, we take its next pointer, so for example a previous.next, and we point that to the node after the one we want to delete. If we take this next pointer and point it to the one after it, that breaks this direct link here between B and C. So this goes away. The only thing that's pointing to data, if we have, for example, a current, once that goes out of scope, that node then gets garbage collected. The way that we're going to do that is the same way that we saw with remove last. We're going to have two different pointers. We're going to start with a previous, and we're going to have a current. And we're going to move those through so that we end up with previous pointing to B and current pointing to the node that we want to delete. Okay? Again, just like our remove last, we need to worry about our 5 boundary conditions. If we have an empty list, we're not going to be able to find the thing that we're looking for, so we can return null. if we have a single element list, we've already seen this before. So let's say we have a single element list. Here it is. If we have a single element list, and this is the thing that we want to remove, what are we going to do? We're just going to remove first, right? It's the same as when we did remove last. We've already got our nice, beautiful remove first code. We've spent hours debugging it. We've run tests backwards and forwards. We know that remove first works. Remove first works for single elements, for empty lists, for everything. Let's use it. We don't need to rewrite that code. So if we have a single element list, we can remove first. What about if we're working at the beginning of the list? So if we're working at the beginning of the list, now next points to another node. And this is the thing that we want to remove. We're going to try and remove this person, this node. What are we going to do? Remove first. Yeah, it's the same thing, right? It's exactly the same situation. The way that we know that we're operating at the beginning of the list is that current is pointing to head, and the other way that we know is that previous is pointing to null. Okay, so we've got two different tests. We can either test if current is equal to head, or we could test if previous is equal to null. Either of those will tell us that we're at the beginning of the list. What about if we're trying to remove something from the end of the list? Now we want to remove D. We found out that D is the thing that we want to remove. What are we going to do? Remove last. Here's current, here's previous. If current and tail point to the same thing, we can just call remove last. Our remove last method works. We've just done it. We've debugged it every which way that we possibly can. So we can use remove last, remove first to handle the beginning of the list and the end of the list. And then the middle of the list is the situation that we're going to deal with finally. So the way that we're going to do this code is we're going to have our same previous and current pointers. So let's set those up. Node E current is equal to head, and previous is equal to null. Cool. We're set up. Now the only thing that we haven't talked about, the last thing that we have to figure out is what if we're looking for an object in our list. We're looking for an object in our list and we don't find it. What's our stopping condition? So we're going to start with previous equal to null, current equal to head. We're going to set previous to current, current to current dot next. 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 When we get to this point, we've checked everything. If we stop here, where previous is not the last node, but the one before it, and current is the last node, so previous is the penultimate node, current is the ultimate node. If we stop there, then we don't check to see maybe this is the thing that we want to remove. Maybe the last node is the thing we want to remove. So we need to keep going until current becomes null. When current is null, we've looked at everything in the list and we haven't found what we're looking for. Okay? So a while loop, while current does not equal null. Okay? The first thing we're going to do is we're going to say, is this the thing that we're trying to remove? Is this the thing that we're trying to remove? So here's our if code, if comparable. That's my best American accent right there. That's pretty lame. Comparable. Whatever it's called.
Compare, like proof.
Comparable. If comparable current.data dot compare to object, or does it matter if I compare object dot compare to current dot data? Rhetorical question. Is equal to 0. So if those two things are equal to 0, or if that comparison is equal to 0 rather, so now I've found what I'm looking for, okay? I found what I'm looking for. So this is where I need to think about my single element list, working at the beginning and working at the end. So let's start with if current is equal to head, we're working at the beginning. We can just return remove first. As long as remove first returns an E, we're returning it, it's all good. We've debugged remove first, we don't have to worry about it. This one test, if current equals head, return remove first, handles both a single element list, because current and head are the same, as well as tail, and it handles working at the beginning of the list. Okay. Our remove first method checks whether head is equal to tail, and if that's true, sets them both to null. We don't have to remember to do that here. We've already done it. So by using another method that we've already written, we've already debugged, we get the advantage of not having to remember about our tail pointer. Our remove first also deals with current size. We don't have to remember to do that. If current is equal to tail, return remove last. So again, we're returning. Once we return, we're out of there. We don't consider any of this other code, okay? So if it's not the first element and it's not the last element, it must be a middle element. So now we can set current size to 1 less than it is. Now we can do previous.next is equal to current.next. Okay. So we're taking previous.next and setting it to current.next. So that deletes the pointer from previous to current. So now the only thing pointing at the node that we're deleting is our previous pointer. Is our current pointer. And now we can just return current.data. Okay. So if we found what we're looking for, we check to see if it's the first thing, if it's the last thing. Otherwise, it must be in the middle. We delete it. If we're not what we're looking for, we just set previous is equal to current, and current is equal to current dot next. That just takes us through the loop. Previous equal to current, current equal to current.next, previous equal to current, current equal to current.next. That goes all the way through until current is null. Once current is null, that means we've checked everything to see if it's what the thing we want to look for. And if it's not, we say, sorry mate, your stuff's not here. That's my English accent. And we just return null. Okay, so there's a remove method. There's a few things I want to point out with this remove method. So the first thing you need to double check is that the remove first and remove last have the same signature that your remove method also has. The remove method may have a Boolean, or the remove first or remove last may have a Boolean. Okay. The second thing that I want you guys to think about is, do you need these 2 lines of code? Do you need to check whether current is equal to tail? I'm not going to tell you the answer. I want you guys to think about it. We've looked at a single element. We looked at the beginning. We looked at the end. We worked on the middle. What about an empty list? What happens with an empty list? Remember, when we have an empty list, head is null. So current starts off null. Oh, that's not very clear. Current starts off null in an empty list. So in an empty list, current is null, while current does not equal null, but current is null. So in an empty list, we don't do any of this. So we skip right down to here and we just return null. So we don't need a separate check for an empty list. That's actually built into this while current does not equal to null, right? So we've checked our empty list as well. And one of the things I need to emphasize is here we're checking for current not equal to null and not current.next not equal to null. If we stop when current.next is not equal to null, we don't check the last element in the list. Okay. So in the remove last method, we stopped at current.next equal to null. In the remove method, we stop at current not equal to null. It's a really important distinction because one will check the last element and one will not. Okay. The other thing about this is that we're given an object and we're asked to return an object. And it's important when you do that, when you do this code, that you return the object that you've stored in your linked list and not the object that you've been given to test. And the reason is because often we have something in our linked list, an object in our linked list, and we want to know more information. For example, if the object in my linked list, let's say it's a person object, or student object maybe, and that has a red ID. And my compare to uses 2 red IDs to say this is the same person or not. But my person object may also have name and email and other information. And so my linked list may have the full piece of data about the person. If I want to remove that person, all I need to know is their red ID. I don't need to know this other information, but I may want to do something, act on that. So what I can do is I can create a new person, assign it a red ID. It's a person, so it's an E. And my compare to method checks by the red ID. It doesn't look at any of this other stuff. It says, okay, this is the same person, their red IDs are the same. So I return the one on my linked list that has their name, their email, their physical address, their phone number, their GPA, all of the other information about them. The same's true with processes running on your computer. Maybe you know the process ID, but you don't know anything else about the process, the command that was used or how much memory it's using or other things. And you may want to get back that other information. Okay? So it's important when you're passed in an object, you don't return, here you don't return object. You return the thing that's sitting on the list or on the data structure that you're using. All right, so we've looked at remove, and let's look at how we find something. And so, for example, a contains method. So I'm going to draw my linked list again. My signature for my contains is public Boolean contains E object. So how am I going to know if my list contains the thing that I've been given to check? I'm just going to use my compare to method right here. Yeah? I'm going to use the same compare to method. And so according to the documentation, according to what I want to do, if my linked list contains this object, I just want to return true. I don't want to delete it. I don't want to remove it. I just want to return true. It doesn't matter if it's the first element. It doesn't matter if it's the last element. I'm not altering current size. So I can get rid of this test to see if it's the first element. I can get rid of my current size because I'm not deleting it. I can get rid of deleting from the middle of the list. In fact, all I want to do is use this comparable method, and if it's there, I'm going to return true. Because all I'm doing is just checking, I just need to know, is this what I'm looking for? Is this what I'm looking for? Is this what I'm looking for? Then I don't actually need to know the thing before, because all I need to know is if it's there, right? So I can get rid of this previous equals current. I can just use current equals current.next. Because I've got rid of that, there's no other place of code where I mention previous, so I don't need to bother with previous. And if I get to the end and I haven't found what I'm looking for, I don't want to return null. I want to return false. So my contains method, my find method, my has method, whatever you want to call it, is pretty simple. I just set a current pointer to head. While that doesn't point to null, I check and say, is this what I'm looking for? If it is, I return true. If it's not, I move it forward. Otherwise, and when I get to the end, I return false. Wow.